Okay, so we have another electrostatics problem here. This one deals with a parallel plate capacitor instead of point charges, but a lot of the stuff about forces and fields is going to be the same. So the first thing is we're asked to sketch the direction, or actually just draw a single vector to show the direction of the electric field between the plates. And that's not a very good straight line. So there's the top plate, there's the bottom plate. Actually, I should put the gaps in it because I'm going to need them. So this is point A, this is point B, this is a distance D, and actually I'm going to change color for that one. The path of our electron got some velocity v, and there's an angle there, theta. Right? Okay, and so this plate is connected to a battery where we have the minus side and the plus side labeled for us. So this is the minus plate and this is the plus plate. And we're also told this is like plus y, right, upward. So the negative plate is sitting above vertically. But we're told to ignore gravity, so that won't matter till the end of the problem. Okay. So we need a direction for the electric field. And we know the electric field always points towards negative charges and away from positive charges. And we know in a parallel plate capacitor, the electric field is perpendicular to both plates. So the electric field must be something like that. So anything that goes from the positive to the negative and is perpendicular. Again, I haven't drawn it perfectly, but that's the idea. So now we have an electron that we're considering that's in that electric field. We need to draw a free body diagram for it. So our electron right there, and we have to think about what forces there are. The first is we're told to ignore gravity, so that one's out. It's not in contact with any surfaces, we don't have any normal forces or anything like that. There's no friction. We don't have any current flowing, so there's no magnetic forces either, right? Stationary charges don't do anything with magnetic forces. So there's only one force, and it's the electric force. But the trick here is that this electron is negatively charged. So the electric field shows the direction of the force that a positive charge would feel. This is a negative charge, so the direction is opposite. Okay, so now we just need to draw in the path that an electron coming in at point A, what path would it follow to make it out through point B? And as odd as it seems, this is essentially a projectile motion question, right? You're launched, your electron is launched at some angle relative to the horizontal, that's that theta value, and there's a downward force, just like gravity. In this case, it's the electric force, but there's no difference between naming a force gravity and the electric force, and so this free body diagram right here, right? That's the exact same sort of free body diagram that you draw for projectile motion. So the conditions are the exact same, so the path is going to be the exact same. You're going to get a parabolic type path. So it's going to come in, kind of curve around, and make its way back out. Right? So it's going to go kind of like that. And again, it doesn't have to be perfect, but you should make sure to indicate it's not a triangle, it's not a straight line, it's not doing anything weird. It's essentially just projectile motion. So that parabolic path. Okay, so that's sort of the drawing half of the problem. And if you've done a good job on that, parts B, C, D, and E are a lot easier because you kind of have an understanding of what's going on. You know what forces are involved, you know the path it's going to follow, and you kind of know a little bit about how it's behaving. So we need an expression for the magnitude of the acceleration. And so we need to use Newton's laws. The sum of the forces equals ma. And we're allowed to use m to represent the mass of the electron. So look at our free body diagram. There's only one force, which is the electric force. And we can divide by the mass. So we're getting there. But we're not allowed to write the electric force as one of our answers. We are allowed to use the electric field and the electron charge, though. And we know that the force equals Q times the electric field. Right? That's that substitution. And now this is going to be our final answer, right? That's the acceleration that the charge feels. And we know what the direction has to be because we know what the direction of the force is, right? So it's an acceleration downward. But we're only asked for the magnitude, so we don't put a negative sign there. But remember, this is an acceleration that's sort of downward in the negative y direction. So part C is, again, sort of, it depends on how well you recognize this is essentially a projectile motion question. Because what we're really looking for in some sense is a time of flight. And so we have linked kinematic equations, right? The x motion and the y motion. So the easiest way, I think, to do this, there's many ways, depending on how much you remember about kinematics, but the easiest way is to note that this point, like right there, here, Vy equals 0, right? It's instantly at the top of its motion. Vx never changes, but halfway through the motion, Vy equals 0 at the center and top. So if we could figure out the time, or actually, hang on, let me restart that. So we know that the acceleration still the wrong way. So we have an equation for kinematics, V final y equals V initial y plus ay delta t, right, the time that it takes. The final y velocity here is that midpoint, so that's 0. The initial is just V sine theta, right? We had this angle initially, the initial velocity, and then the sine gives you the vertical part. The y acceleration is simply, so it should not be plus, but it's simply what we found in part B. And I'm going to use negative because now we do care about the direction. Right? And so now we can figure out what the amount of time is for the electron to follow what I'm going to kind of retrace, just this half of the path, right? That half of it, from the start to that midpoint. So we just rearrange. We get V sine theta equals QE over M delta t. And so delta t equals mv sine theta all over QE. And if you, again, remember, projectile motion when there's no air resistance is symmetric, so the amount of time it takes to follow that blue part is just doubled to get the whole thing. And so I'm kind of out of space, so I'm just going to multiply it by 2 right here, because we need to go from the start to the midpoint and then the midpoint to the end. And so it just is this, 2 mv sine theta over QE. Which is kind of an ugly expression, but it's using all things we're allowed to, so it's fine. All right, so this next piece, we need to figure out what the value of d is, such that the electrons sort of make it out successfully. And this is, again, a projectile motion type thing because the horizontal velocity is constant. So v equals vx equals v cosine theta. And if we want to know how far we travel, right, delta x equals Vx, write it like that, so Vx delta t, right? How far did you travel is based on the constant speed you're traveling and the amount of time it takes. And we just found delta t, so this is V cosine theta, and then we need delta t, which is 2mv sine theta all over QE. And this is already done. I mean, you can clean it up a bit, but writing 2mv squared sine theta cosine theta over QE is a little bit nicer, but you know, it doesn't really matter. Once you've recognized the horizontal velocity is constant and sort of plugged in all those components, then you're really pretty much done. Okay, and then finally part E. This one is an explain and describe, so there's no actual calculation. But let me go back to the pictures. So if we added gravity, this free body diagram is going to change, right? There's another force, right? This is the force of gravity. We would add that in. That means that this acceleration that we got right here is going to be a bigger number, right? They're in the same direction, right? So this is like a plus g, right? So if the downward acceleration is bigger, then that means that we spend less time in the capacitor plate, right? Because delta t is based on that acceleration. If a goes up, and then delta t has to go down. And so, if delta smaller, then we see here that delta x must be smaller. And so that means that the distance d that we travel goes down. So the kind of reasoning is that a is bigger, so delta t must be smaller, so d must get shorter. And that's basically what you want to write right there. You notice how the effect of gravity changes the acceleration, and then kind of trace that through your work.